Hi everyone, thank you for coming to my talk. My name is Xiancong Luo. I am second-year PhD student at the University of Edinburgh. So today I am going to talk about open quantum system in cosmology, and this is an ongoing work with my supervisor Sudhasatwa Brahma and Jaime Calderon. So there are 4 parts in my talk. The first one is our current understanding of early universe, including the observations and models. The second one is what is stochastic inflation and why do we need it? The third part is a short review of open effective field theory, which is the tool we use to study stochastic inflation. And the last part is the results and conclusion from our calculation on a specific model using open EFT methods. So let's get started. So based on the observational results, lambda CDM model is the concordance model of our universe, and primordial fluctuations are observed to be nearly scale invariant, Gaussian, and adiabatic. The minimal framework to explain these early universe observations is the single field slow law inflation. But regarding to this inflation model, there are actually quite a lot of questions. The first one is why is the quantized perturbation become classical after re-entering the horizon? It is a question related to quantum measurement problem, but practically we can also use decoherence to see where does this classicality become apparent. Another question is that since the scale of CMB we observed is quite limited, what is the behavior of other scales? Is there the same with CMB, or do they have other peculiar behaviors? The third question is about how to deal with back reaction from fluctuations to the dynamics of background. So we know that quantum fluctuation will grow into large structure such as galaxies, and the distribution of galaxies will definitely have a back reaction to the evolution of the whole universe. And last one, do we have a non-perturbative thing to keep track of large fluctuations? Because most of the calculation we do to CMB perturbations is the standard perturbation theory. But once you go to higher perturbatives, then the standard perturbative theory is invalid. Sorry, I'm going to. So stochastic inflation is introduced by Starobinsky at 18th last century. We know curvature perturbation become highly squeezed after horizon crossing. And this is the Hamiltonian for the Mukhanov-Sasaki variables. We can divide it into 2 terms. One is the usual scalar field in flat space, and the other one is the squeezing term due to curved space. After it crossed the horizon, k will be much smaller than z prime over z. So this term will dominate, and the initial Minkowski vacuum will become highly squeezed between k modes and minus k modes. And in this limit, in this squeezing limit, quantum mean values for most observations is almost equal to stochastic average. So in this case, we actually can describe these quantum effects using classical and stochastic theory. So how do we do it? We basically establish EFT for long wavelength mode and cross-grain these short wavelength modes. We see that this quantum fluctuation at squeezing limit can be written as a sum over the cross-grained field, which is the long wavelength modes, plus the effects from short wavelength modes. And specifically, we can write them into the Langevin equation. We see that the cross-grained field has a dynamical effect coming from the short wavelength modes. And in squeezing limit, these modes is classical and stochastic. And in the research of stochastic inflation, people usually assume this is the white noise. So we see that in stochastic inflation, we use EFT methods, but the EFT used there is not Wilsonian EFT. The reason why it is not Wilsonian EFT is that in cosmology, there are UV-IR mixing. So the quantum fluctuation used to be in IR section will become very, very big after inflation, and it becomes an IR effect. Did I say IR or UV? Well, yeah. And there in general no energy conservation in cosmology, because imagine that our universe expand and there will be incoming of dark energy to support the accelerated expansion. So the universe we observed is definitely not energy conserved system. And the third one is information transfer. So the EFT used here can be non-unitary and non-Markovian. Non-unitary means that the quantum states doesn't have to preserve the probability conservation. And non-Markovian means that there are memory effects on your evolution. So usually when we write down the equation of motion, the effect is coming from the same time points. But if there's a memory effects coming from the time long ago, then we say it's non-Markovian. This is why we need open EFT program to study cosmology in general. So what is open EFT? The first aspect of open EFT is that we need to choose what is the system we are interested in and what is something else, and we call them environment. There's no particular separations. It is always based on your model and your system. So the system environment separation can be horizon and the skew, the different fields, and every observable and unobservables. For example, you can separate the system environment in terms of momentum scales. For those, the scale are larger than the Hubble radius, they are considered to be system, and every other models are just environments. And the second step is to chase out the environment degree of freedom. So if we have the density matrix of our whole system, this is just the Heisenberg equation. And later on, you solve this density matrix, and then you chase over all environmental degree of freedom, then you will get the density matrix for the system. In general, there are additional terms compared to Wilsonian methods that captures the non-Markovian effects. We see this equation here. The first term corresponding to the Markovian methods terms. So it basically looks like the normal Heisenberg equation, and the Hamiltonian here is the Hamiltonian of system, and a unitary correction from the environment degree of freedom. And there are some additional term here. This additional term is what we call non-unitary effects. They are usually divided into two aspects. One is dissipation, meaning there are some energy exchange between system and environment, and the other one is diffusion. This is the quantum entanglement exchange between system and environment. So this equation can account for these two non-unitary effects. And in our model, we use time-convolutionless projection operator methods, which is one kind of methods of open EFT. Its advantage is that it can capture the late-time behavior of our system. So we follow the model by Boyanovsky in 2015. It is a system with two scalar fields. One is the minimal coupled massless scalar field. We treat it as the system field. And the other one is the conformally coupled massless field, and we treat it as the environment field. Why this model is interesting is that the conformally coupled scalar field is a proxy for small scales in the framework stochastic inflation. So it doesn't it doesn't feel how the curvature changes. So basically, these environment fields will always behave like a free field in flat space. That's why it's a good proxy for small scales perturbations. And the coupling constant lambda is said to be small for the purpose of perturbation analysis. But eventually, we can go beyond perturbation analysis by a program called resummation. In short, we can get TCO equation, and this is basically the same as what we have said. There is a unitary term, and there's two non-unitary terms. One is related to the diffusion, and the other one is related to the dissipation. So it's worth noting that the diffusion and dissipation terms sometimes can have memory effects, meaning sometimes they can be non-Markovian. There is another aspect I want to emphasize is the circular divergence and late time resummation. So typically, if one solves the open EFT equations, you will get late time divergence problems, denoted as circular divergence. This is because we cannot turn off the gravity effects, so the gravity effect will always apply to our system. This is the example we can see this effect. So basically, if we are trying to use perturbation theory, we need to expand this evolution operator into these terms. But if you go to late times, this t will be like infinity. So there will be divergence on these evolution operators, and then every observations you calculate will be divergences. For example, in our case, these D's and deltas corresponding to dissipation and diffusion effects diverge at late time. So this means a breakdown of perturbation theory. However, these circular divergences can be cued in a specific way. So if the equation of motion, for example, our TCO equation, is written in time local form, meaning that there's no other time variables in this equation, there's only one time dependence, then we can resum and extend the result to late time in a convincing way. So here's an example. We have the equation of motion in time local form, but the problem is that we calculate this lambda in a perturbative way. So the best we can get is actually this solution, n0 times 1 minus lambda t and plus some corrections. And this is valid in a small time range. But we can always change our initial conditions and we will get another solution for this and the later one. And eventually, if you believe that they are valid in a small range, and you can always use that small range as an initial condition to continue your solution, and you will get the 4-time solution, which is a good approximation for late time behaviors. And we get this non-divergent term, non-divergent solutions. So what we learn from the result? First one, in the framework of stochastic inflation, late time divergences are from time local terms. And these time local terms leads to the white noise going into the equation of long wavelength modes. However, we noticed that in our case, non-local terms are responsible for divergences and for the later approach to the resummations. So this indicates that we should modify how we co-screen the quantum fluctuations in stochastic inflation. We should use colored noise instead of white noise. The second term we can know is a prediction of late time behavior of power spectrum. Basically, we use the TCO methods and we extend to late time using the resummation methods, and we get the second order behavior of power spectrum in terms of the number of epoch. The third one is the purity. So purity is the measurement of entanglement between system and environment. It is a measure of how the quantum information flow between system and environment. We see in general, for our case, the purity decays quickly into zero, so the quantum fluctuation flow into the environment with very quickly. But we also notice there's a fluctuation in purity, meaning that there are small non-Markovian effects coming from the environment because the environment is not big enough. So the way system if affect the environment will change the behavior of environment, and it in turn change the purity outflow behavior. So I want to make some points and conclusions for my talk. The first one is that cosmology is a natural playground for open quantum system. There are always some environment that is not important or we just cannot observe, but they will have impact on our system and impact on our observations. The second one is that, as I said, non-unitary effects coming from this environment may have experimental predictions on our observations, which is very important for our next generation of observations. The third one is kind of what we want to do in the next step, is the tail of probability distribution function of curvature perturbation. This means that we are going to go beyond the standard perturbation in cosmology using this open EFT and to probe these large curvature perturbations that cannot be described in our standard perturbation theory. And there are the candidates for primordial black holes, and maybe we can make some predictions for the abundance of primordial black holes. Thank you for your attention, and see you.